Hello everyone, this is Jay Gupta. I'm a computer science engineering graduate with 2 years of industrial experience in data science and machine learning. I've also worked as TA for Introduction to Python and Statistics course in the past. In this session, we'll talk about what is Autograd, gradient descent, and Pytorch neural network model. Let's start with what is Autograd. Autograd is a computational framework that is used for automatic differentiation in machine learning. Essentially, it allows developers to compute gradients automatically for complex mathematical functions that are commonly used in neural networks. Now, you might be wondering what exactly are gradients and why are they so important in machine learning? Gradients are essentially derivatives which are used to measure the sensitivity of a function with respect to its input variables. In machine learning, we use gradients to update the weights of a neural network so that it can learn to better predict the output for a given input. The process of computing gradients can be quite complex, especially for large neural networks with many layers. Traditionally, developers would have to manually derive and implement the gradients for each layer, which can be time consuming and prone to errors. AutoGrad helps to solve this problem by automatically computing the gradient for us. One of the key benefits of AutoGrad is that it makes it easier for developers to experiment with different neural network architecture. Since the gradients are automatically computed, developers can spend less time worrying about the complexities of gradient computation and more time focusing and building on testing their models. So now we'll go through a simple building of a computational graph, which is a single neural network propagation with the activation function, and we'll be calculating the loss for that. So you can see that this code defines a simple computational graph using the class simple graph. This class takes two arguments W and V, which are the initial values for the weight and bias. The init method. So yeah, so we're initializing. So the init method initializes the class and sets the value of W and V as Pytorch tensors with the required grad set to be true. This means that the gradients will be computed during backpropagation. So the next function we have is forward. So the forward method performs a forward pass through the graph. It takes a tensor x as an input and returns a tensor predictions. The forward pass involves calculating a prediction using the weight and bias value and passing it through a tanh activation function. The tanh activation has a steeper gradient around 0. This means that the tanh activation function can provide better gradients for backpropagation, which can lead to faster convergence during training. So you can see we'll be calculating our prediction using the simple linear regression model and a tanh activation function. So, okay. So this is a tanh activation function. Let's pass our what we'll be using to know. So this is our x, which we have already taken in the input. This is our input. Then we multiply with our weights and then with bias. Also, since we're using the Pytorch model, we have to denote torch dot tanh. So now it's fine. Now the next we have function we have is a square loss function. So the square loss method calculates the square error loss between the predicted output and the actual target output. So it takes two arguments, also called tensors, y true and y predictions as inputs, and returns the L2 loss. So now let's keep the value for the loss one. So we have so for this we can write y underscore true minus y underscore prediction, then square root of it. So yeah. So now at last we are initializing our input with 1 and the target is 7. So now let's uncomment this code and run it to see what will be our outputs and the loss. So we are initializing a class with weight minus 0.5 and bias 0.5. Then we're in this line, we're calling our forward function with a feature. Then in the square loss, we're calculating the loss what between the target and the prediction. So let's see what we get as an output. So you can see our initial weight was minus 0.5, bias was 0.5, input was x equals to 1, and output was 7. So it gives the prediction as 0.0, which is totally wrong, and the loss is seen as 49. So it's very high. So you can see the reason behind the prediction wrong is the loss is very high. So it